close enough? Do I need to adjust this? Is that even? Is this even? Seems good? Okay. So hello, everybody. My name's Chandler, and we're going to be talking about 3D projection. Before we start, who am I? What do I do? This is a picture of Earth from a satellite. That's my day job. I do satellite imaging and the geometry of different images and how they align with each other. And kind of the reason that's interesting is that computer graphics and real imaging have a lot in common and some things that they don't have in common. And it's kind of been fun for me to figure out, okay, why do the people in the computer graphics community and the architecture community who share all this same camera geometry interests do things a little bit different than we do in the actual imaging world. So why am I going to give this talk? Really because I think this is a really fun way to learn computer graphics. It's super tangible, and you can sort of control the entire chain of producing something end to end in a way that you can never do with a printer that is some insanely precise microcontroller putting out nano dots everywhere. This is something you can grab, you can hold, and honestly, it's not that many points, so you don't need to push things to GPUs. You don't need to worry about parallelism. You can loop over these things in whatever programming language you want and really write your own renderer and do everything from scratch and teach yourself how you might have invented printers or CRT displays if you were the first person to do it. And I think that's what's really exciting about this. So we're going to talk about some first principles to get started. So 3D rendering for pen plotters. There's three major topics if you set out to do this that you're going to run into. The first is projection, and that's what we're going to focus on today. And that's okay, you have something that's three-dimensional, but clearly the screen is two-dimensional, so something sort of interesting had to happen there, and that's projection. The second thing you're going to be is I can see through my object, and how come I can see through it, and I can't see through real items? And that's hidden line projection, or hidden line removal, and it's really interesting, and we're not going to talk about it at all, but I will give some tips for some software you can check out at the end. And the last thing is textures. These cubes, their internal structure is sort of like a triangular mesh, but they have emoji on the side. And that's not really inherently part of the structure of those little planes there, but they're there anyways. And that's a texture. That's something you put on your object that you want to display as opposed to what it naturally is. That's also not the point of this talk, but you should remember these three things if this is what you're going to do. So hopefully, I think projection is the fundamental first thing you want to tackle, so that's what I'm going to talk about. So this is the thing I'm not talking about, hidden line removal. You've got a wireframe bunny, and you can see through. Over here, it looks more solid. You can't see the other things. It's almost like the triangles are solid faces. That's hidden line removal. And I'm not going to use it in this talk for the bunny, but I'm going to use it in a few other places. But yeah. And this is what textures look like. So here's some objects where internally they were triangular meshes. Externally, they have nice, pleasant lines, and the edges are a little bit thicker, and that's all texturing, and that is not what we're talking about, but you should know that it exists. So our area of study today is going to be this bunny, this wireframe model. For our purposes, the bunny could effectively just be a bunch of points. The lines between it are sort of implied. The data structure is just a bunch of points. And all you need to know to project things is the points. But the lines are sort of there because you probably are plotting these as wireframe models. So we'll just leave the bunny so it looks more like a bunny because I think it's kind of cute. So let's just kick it off. What is the simplest thing you can do to take a 3D object and make it two-dimensional? Well, if you imagine a plane beneath it, and if you were just to drop everything onto that plane, maybe if it had 3 coordinates and you just deleted the z coordinate, that would just all of a sudden flatten it out. There used to be 3 coordinates in all these points. Now there's 2. By deleting something, that's called an orthographic projection, and you're projecting onto this sort of XY plane, sort of one of the cardinal planes you've got in your 3-dimensional space. And the reason it's called orthographic is because for 10 of the sample points, I've sort of drawn a connection between where they were before projection and where they were after projection, and that angle between the plane they're on and the line of projection is 90 degrees. And that has to be 90 degrees for it to be an orthographic projection. And that's a word we're going to talk about a lot. And this type of projection isn't the only type of projection, but it's what we're going to focus on. Now, of course, you don't have to just project onto this XY plane. You could also project onto either plane. And as you can see and pretty much intuitively know, you get a slightly different view of the bunny. So, if you have a 3D model, you probably care about which view is going to be most interesting or aesthetically pleasant or show off the most about it. So you're going to want to be able to choose which plane you project onto. It's not always going to be satisfactory just to project onto the Z plane. So we're going to talk a lot about projecting onto planes that aren't just the easy ones. Like this one. This is a random plane sort of floating in space near to this bunny, and maybe it's hard to convince yourself, but this is still an orthographic projection. So this bunny is being sort of thrown against this plane, and those lines meet that plane at a 90-degree angle. Here's a couple views of it. Still, maybe you can convince yourself, maybe not, but it's still orthographic. Orthographic has some interesting properties. It doesn't matter how far the plane is away from your object when you project it. So if you move even any of that second plane right there on the right is even further, and the bunny has a different perspective, but it has the exact same magnification. So that's a pretty important thing, is that it doesn't really matter how far you are away from this plane, and that can be good and bad. Okay, so here's where things get really cool. So instead of just sort of throwing all the points directly at a plane at a 90-degree angle and doing orthographic projection, you could pick a point, and this little plane here represents sort of a point, even though it's a little plane, and called the center of projection. And what you do is you draw a straight line between the plane you want to project onto and the object through that center of projection. And this gives you a perspective projection. And perspective projections are way more complicated and pretty interesting. So if you notice on the right there, the magnification of the bunny is quite a lot smaller. And on the left, it's quite a lot bigger. And that's because the bunny is closer to the center of projection on the left. This should be pretty intuitive to you because it's how cameras work. If you're up close to something, it's large. If you move very far away, it gets smaller on the plane of projection, which in a camera's case is your sensor. And you can kind of see why that is. It has to do with these angles. The object starts converging towards the center of projection, which in a camera is your aperture, so it's the end of your lens. And then it starts diverging, and you catch it with a plane, which is your sensor. So in this case, these two cameras, this distance between the center of projection and the plane there, that's sort of like the focal length of your lens. And if you move back farther, it's going to project smaller on the back of your sensor. So this is kind of cool. If I increase the focal length here, you can sort of see pretty intuitively through the angles of the rays that you get a larger magnification of the bunny. And so this is kind of like, oh, I just like zoomed my lens in, and now it's bigger, even though I'm farther away. There's two ways to make things bigger. You can increase your focal length, or you can get closer. It's called zoom with your feet in photography. So you might also notice that this object is upside down. So that's important to remember. Earlier with the orthographic projection, everything was right side up, but now the lines sort of go from the top, they cross through the center of projection, they hit the bottom of the projection plane, so everything's like flipped upside down. This occurs in cameras as well, or in your eyeball. Like when you're looking at people, their head ends up on the bottom of your eyeball, their feet on the top, everything is upside down, and your brain just flips it around. So that's what's going on in your eye. But computer graphics is not constrained about physical things. There's no glass involved, so we can do some pretty interesting things, like put the center of projection behind the projection plane. So this confused me forever because I'm a camera person, and I didn't expect the focal length to be negative because, it's made of glass. But in this case, and it turns out in almost all of computer graphics, the way they do it is they put the projection plane in front of the center of projection. So these rays are still headed towards this center of projection point, but then they catch it with this plane in front. And this actually makes the image right side up again, which is very convenient. And a lot of things that happen in math and programming are done for the convenience of avoiding negative numbers and upside down things and all kinds of stuff like that. So this is something you're going to catch if you look at Wikipedia. You'll probably see this picture anywhere you go. You start learning about computer graphics and rendering. This little pyramid thing is called a frustum. And the first time you see it, you're like, okay, so everything inside this volume is what's going to be rendered. And I guess it's a little bit in front of the camera. So there could be items that are in front of the camera, but they're not in the rendering volume. And it's like, no, actually that's the whole camera. It's just a camera with negative focal lengths. And this thing they're representing down here is the center of projection that's negative behind that plane. So if you see this, you can still think of that yellow thing as sort of like the CCD or the sensor on your camera. And you just imagine it being like a backwards lens. Nobody explains this very well, and it took me quite a while to really be like, oh, okay, I get it. Cool. So center projection can be negative. One interesting thing about perspective projection is as you increase the focal length, the rays start to become more, they get closer and closer to being 90 degrees. So they get closer and closer to being orthographic. This is pretty cool because if you have your software set up to do perspective projection, but you want an orthographic projection, you don't want to have to go figure out the new matrix or whatever, you can just set in a very extremely long focal length in your perspective projection, and eventually you're back to orthographic projection. I use this all the time. I'm lazy. I just I want an orthographic projection. I'm just using a super high number for my focal length, and then all of a sudden I get orthographic instead of perspective, and it's all good. So this is kind of an example of if the focal point was at infinity. It's infinity away. It hits this plane. Then the rays are now hitting at a 90-degree angle again, and you're back to orthographic. So I couldn't really call this out, but this is kind of meta, because if you look at any of these scenes, right, I've got these two cameras, but there's also a camera like right here, and that's the camera that's like rendering this scene. It's kind of like the meta camera, the third one, that is doing that. There's a plane, and it is the screen that you're seeing, and the whole of this scene is being caught on that. And that is actually, I chose for this an orthographic projection, which is why everything looks fairly regular. You can still really tell those are rectangles, even though they're at an angle, and the bunny looks pretty normal, and nothing's too messed up, because these are all being projected just parallel straight onto like a plane, which is very literally this display you're looking at on is where that other plane was that all these points are hitting. But if I were to use a perspective camera to render the scene, well, then the distance that everything is from the plane would impact its magnification, and now things go all sorts of crazy. Those rectangles are now, you're not even sure were they always rectangles. I can't really tell. This is the equivalent of using a super wide angle lens. A very short focal length, you're getting a ton of perspective effects, and you really want to know about this stuff when you're rendering your plots, because it's a very big decision in terms of the artistic style of your plots. Is, do I want my buildings to look all funky like a person might have seen them, or a wide angle lens, or it looked very architectural and all the angles line up and everything. And so for a long time I was making my maps with perspective projection on accident, and then I realized what I was doing, but I was like, oh, it's my style. I'm just going to keep it that way because they look kind of weird. But I probably, when you're making maps, you tend to want to use an orthographic projection because you don't really need the realism of perspective when you're like rendering something so high up that no one would really be there anyways. So you really should think about which projection you want to use. Oh yeah, this was just to flip back and forth between these. So I don't want to leave anyone behind here, so we're going to go over some basics. I could have also titled this talk A Little Bit of Linear Algebra Goes a Long Way, because it really does. So let's talk about matrices real quick and transformations as matrices. So this XYZ on the right here, that represents one of the vertices on the bunny, one of the points that we're trying to project from the bunny onto the plane. And this matrix represents a transformation that's going to put it on that plane. And the XYZ over here represents an XYZ point still in 3 dimensions that is on that plane. Some sort of transformation. And the reason it's a matrix is just a function that's so special you only have to list the coefficients, because it's just assumed that it's so obvious that everyone will know what the function is. So I've written down the function, and it's just, you take all of those coefficients and everything on the left becomes, you build it up out of a combination of the inputs that are scaled by some value. That's a linear transformation, and we just assume that when you see the matrix, you think function that does that. So hopefully, I'll go back to this a little bit, but it can be a little bit hard to remember exactly how it all lines up. You kind of can just think about, this is a function that takes that and outputs that. These are really useful, because if you have 2 linear transformations, in this case 3x3 ones, you can just multiply them together and get another one with 9 entries that does the exact same thing as both of them, which is really awesome, because you can maybe you have dozens of things you're trying to do, but if you can do them all with matrices, you multiply them all together and you can do it in once. So it's really computationally efficient, it's very elegant, it's what you want to do. So let's look at some matrices. So this earlier one, this orthographic projection, this is the matrix that does it. The x gets picked up by the 1, so x times 1 just picks it off. The y gets picked up by the 1, the z gets zeroed out by the bottom row, and so z goes to nothing, and the bunny gets pancaked onto the floor. It's pretty much the identity matrix. If there was a 1 in the corner, it'd be the identity matrix, and it would do nothing. Along all these other planes, same exact thing. It's the identity matrix with one of the 1s just cut out so that you get sort of thrown onto that axis. It gets zeroed out. So, okay, so this random plane, what's 3x3 matrix that takes these points and plops them onto this? That's what we really want to get at in this talk. So we have to go on a little bit of an adventure. So if we kind of highlight the plane itself instead of the bunny, I've drawn a normal vector to the plane. So this is basically a pole or a line coming out of the plane at a 90-degree angle. And that's pretty much all there is to a normal vector of length 1. And it's going to help us kind of visualize where the plane is going in our transformation. So the first thing we want to do in this little journey is we want to translate the plane so that it's at the origin. So the plane now goes through the origin. I've applied some sort of translation. And importantly, I've moved the bunny with it. So everything came. You could have also sort of moved the origin up. You can really think about moving the origin or moving the whole thing to the origin. It's kind of the same thing. You can think about rotating the bunny. Whoops. Okay, I have to do a lot of flickering in this talk. So Second step, rotate so that the normal of that plane is now rotated up so it's pointed at the z-axis. Now maybe you see where I'm going with this, because the plane that we wanted to project on is now, through two transformations, a translation and a rotation, it's now the z, or the xy plane. We can now project onto it using one of those matrices that we just saw earlier. So boom, we use that linear transformation, we throw the bunny down, now we rotate back, and we translate back, and through the magic of like 5 steps, we've actually projected this bunny onto this plane. And so that's pretty cool. So yeah, here it was again. You translate it, you rotate it, check the bunny down, you unrotate it, you untranslate it. You know, it's like 5 steps here. It's a little bit cumbersome. If we could make it all one matrix, that would be pretty sweet. This is kind of like maybe what we want. It's like, oh, are these all 3x3 matrices? Because then we could just take all 5 of those steps, starting from then. You translate it, rotate it, project it. The -1 means inverse, so unrotate it, untranslate it. Could we do that? Make them all one 3x3 matrix? That would be wonderful. Well, we know the projection can be done like that. The projection is a 3x3 matrix. We saw that. And I'm missing a parenthesis. I didn't tell you this, but 3D rotation can always be represented as a 3x3 matrix. Not only this one. This is rotation about the z-axis. Depends on what axis you want to rotate about. But you can always do a 3x3 matrix. So we're good for rotation. We could find a 3x3 matrix that does our rotation. But we are totally not good with translation. So that translation step was vector addition, not matrix multiplication. To move something down to the origin, you had to add to it. So you took all your points and you did like plus some amount. And the reason that's not a matrix thing is because those linear transformations, the rule of being a linear transformation is that they're not allowed to move 0. If you put the origin through the transformation, it has to come out as the origin. But if you add some amount to the origin, it's going to come out as not the origin anymore. So vector addition and matrix multiplication are entirely different. And so since this is a vector addition step, we can't really chain it together with the other ones, which sort of breaks our ability to make this one nice matrix operation. And it's sort of frustrating. So yeah, we have vector addition, linear transformations, entirely different things, different operators. They don't go together. We do have a name, though, when you want to do sort of a rotation and then a translation, and that's called an affine transformation, because it is really common. It's not unheard of to want to rotate and then translate. You know, spin, look, this is a very common operation. It's just not a linear operation. So it's an affine transformation. You know, it's instead of x equals ax, it's x prime equals ax plus t. So what we really want to do here is we really, really want this to be a matrix multiplication problem, especially in real life with video games where we're pushing like billions of things through the GPU. This has to be a matrix problem. Maybe you don't need it to be a matrix problem for pen plotters. You could just chain them all together, and that's fine, and you actually can. But this talks about how to make it a matrix problem. So let's go whole different world. Just come back to 2 dimensions. This is nothing to do with 3D and just like 2-dimensional square. And let's talk a little bit about 2 dimensions, because this is going to get some dimensional trickery, and it's easier to start with 2. So what we want to do is translate a square in 2 dimensions, right? Pretty simple. Like I said earlier, that's going to be a vector addition. You're going to have some coefficient that you add to every point in the square, or subtract, whichever way you want to go, and it's going to move everything to the side. But can we do it with a matrix? So we can, but first we have to do something I think is pretty interesting, which is rip that square out of 2-dimensional space and stick it in 3-dimensional space at some plane where z equals 1. And I think this is pretty cool because, I mean, you're often reducing dimensions, but you're not very often like taking something and ripping it out of its flatland and like sticking it into a higher dimension for something you're going to do to it. Like that doesn't happen very often. So this plane is just like living there, and all of a sudden it's like ripping you and putting you in 4 dimensions. But we've placed it at z equals 1 in 3 dimensions. And the reason we've done this, very cool reason, is what used to be the origin at the corner of that square. Now that's not really the origin anymore. The origin is at 0, 0, 0, the origin of the 3-dimensional space. So you're free to move it, which means you can do things like move that around without having to break your linear transformation laws. So let's explore that a little bit. So what we want to do is find a transformation, a matrix transformation, that can translate our plane, our little square, along the plane that it's in. Oops. It's kind of hard to do this flickering. Boom, 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 like that, without vector addition. So how does it work? Well, this is the matrix that does that. So our vector addition coefficients, instead of being in sort of a vector addition vector, I guess, they're now the top 2 entries in this matrix. And basically, this is a shear matrix, So you're applying a shear to all of 3D space. And what's going to happen is the x is going to get picked up by the 1, the y picked up by the 1, and then the vector components, they're going to get multiplied by the 1 on the bottom there, and they're going to get added. So they're effectively going to get added to everything. And I've kind of spelled this out here so you can see the math. Because sometimes the visuals work for people, sometimes the math. So this is the equation version of that. So you can see the tx and ty, they're multiplied, but only by 1. So they're effectively just getting added to everything. So it is kind of like vector addition, but in matrix form. And to maybe sort of make this extremely visual, imagine if these planes had been stacked not just at the z equals 1, but all the way back to z equals 0. What does that matrix look like when applied to all of these? It's a shear. So everything gets sheared. And if you notice, the plane that's at 0 stays at 0. So we haven't broken our sort of things at 0 have to stay at 0 rule. Everything gets sheared, but it's a shearing of 3D space that happens to be the translation we desired in our plane that we put everything in. So this is great because we don't really care about the rest of the 3D space. There's nothing in it we care about. We're only caring about the plane, but we're doing everything in 3 dimensions. Here's another angle on that shear, so you can kind of see how it works. Great. So this is pretty magical. We're taking 2D affine transformations, and we're making them 3D linear transformations. And at the end, all you have to do is delete the third coordinate, that 1, and you're back into 2D. So you go to 3D, you get all twisted around, and then you delete the other coordinate, you're back to 2D. You just translated with a matrix, and it's very fast and very cool. So maybe you're thinking ahead, maybe you see where this is going, but we need to go to 4 dimensions. So that was about doing 2 dimensions in 3D, but what we really care about is taking this 3-dimensional bunny and translating it. And there's really no good way to visualize this, which is why I started in 2 dimensions, but we want to do all of our operations in 4 dimensions. And this is really the thing I'm trying to, that took me a long time to get, and that I hope you take away from this, is whenever you go onto a blog or start reading some source code, you're going to see these 4x4 matrices everywhere. And you're going to be like, why are we doing 4-dimensional math when we've got 3-dimensional objects? And it's because you're doing a trick, you're hoisting everything into an extra dimension so you can do translations. So you can compose everything into matrices and make everything extremely fast. So this is the 4x4 transformation matrix. This is the translation component. This would be like a rotation component. You multiply the point, and then at the end, just like last time, you delete the 1, and you're back into 3 dimensions, and it's pretty cool. So now, what we've always desired, we have the matrix to put this bunny onto this arbitrary plane. It's got a rotation and a translation first step. You've got the projection matrix we know and love, where it drops it down to z, and then you have the inverse of the rotation and the translation. It takes you back. You multiply those all together, you're going to get some 4x4 matrix. You can save that, numpy dot your point, and that's going to place it right onto the plane. So that's pretty exciting, if you ask me. But there's a little bit of a hitch with the perspective stuff. So if you go Googling, I need a perspective projection matrix, you're going to notice that unlike on the orthographic one, so that on the bottom row it's 0, 0, 0, 1, there's nothing in 1. So you can just delete that 1, always ends up as 1, you can just delete it. In the perspective matrix, you're going to notice this M here. There's going to be some entry in that bottom row, which means that the last entry of the result is not going to be 1 anymore. It's going to be some value W. And you can't just ignore it. You can't just delete it like you did with the orthographic. What you have to do to get back into 3 dimensions, so if you just want to stay in 4 dimensions, that's fine. You just have a W. That's cool. You can do 4D stuff, but you probably want to go back to 3 dimensions. And the way you do is you take all of the resulting X, Y, and Z's and you divide them by the W. And that division is basically going to make things smaller depending on what W is. And W is going to depend on what Z is, which is how far away things are. So things that are farther away are going to get divided by a bigger number, and they're going to get smaller and smaller on your focal plane, which is pretty much what magnification is. That's sort of the analog of what's happening in the world. Things that are farther are getting divided more and more, and they end up smaller and smaller. So that's the perspective projection matrix. This is the form it's going to take. This is not, I didn't explain how to get to one because it's actually quite complicated. So you're like, okay, cool. The reason I did all this is if you're Googling around for things, the first thing I found on Google to do this stuff was this transformations.py thing, which is a very nice, complete, dependency-free transformation Python thing. And everything was 4x4 matrices. You're like, oh, a translation matrix. Well, it makes a 4x4 matrix and returns it. So now if you run into this stuff, you're like, 4x4 matrix. I know what to do with that. Multiply my point against it, take the 4th value, divide everything. I'm back into 3D. No problem. This is very cool. And the reason they do the translation in 4x4 is so you can multiply it against all the other matrices in that library that spit out 4x4 matrices. They all just compose together very nicely. So almost done here. So now that we can read matrices a little bit, we head over to the Orthographic Projection Wikipedia. This is what I did. And before I did this talk, I was kind of like, okay, I'm nodding my head. This is an orthographic projection, cool. But now I'm looking at it, I'm like, okay, what's going on here? Well, you've got the translation component. It's a 4x4 matrix. You've got some translation happening, but you're just scaling it down the center. There's none of those are zero, so there's no projection going on. So I'm like, okay. And it's also, there's no rotation, because we would have entries sort of in the 3x3 area here. So I'm like, okay, so it's assuming there's no rotation, so it's assuming you're already pointed at your camera, and it's not even doing the projection. And I realized that this matrix doesn't have anything to do with projection. What this matrix does, the one that's listed on Wikipedia under orthographic projection, is it normalizes your coordinates so they all fall in a bounding box that is between -1 and 1. And this is really important for computer graphics because it preps everything for the GPU, so the GPU can start clipping everything outside of that box that's not going to get rendered for space savings. But it doesn't actually have anything to do with mathematical projection. It already expects that you've rotated the scene, and it expects that when you're done with this matrix, you actually do the projection yourself. So, having a little bit of familiarity with being able to read these matrices can kind of help you with the stuff that I think is quite confusing, since this is the main thing listed on a projection matrix wiki page and doesn't project anything. So yeah, it kind of assumes that your scene is already rotated so that it's pointed straight up, so you don't have to do any rotation. It's just going to scale everything down so that it fits between 1 and 0, which is really important if you're doing actual computer graphics and not just plotter stuff. And just so you know, all these near-far things that are parameterized this matrix, they're the components of this little pyramid thing here. So what you would do is you would figure out what the left and right, you'd basically define these two planes here, this plane and that plane, and you'd put them into the matrix, and it would transform this pyramid in your scene into the unit cube, which is a cube between -1 and 1 in your scene. So I obviously didn't go into that very much because this is for if you're doing WebGL or any sort of real renderer, you're in Blender, you're going to have to know this stuff. You don't really have to know this stuff for plotter stuff because you're not pushing anything into the GPU. You can just write this in Python with a few NumPy matrices, which is what I did for all of these scenes. So, but there's a little bit of a hint if you're trying to get into this stuff for real. So this talk, obviously, it's been about projection. I want to give you a couple hints about what to do about the rest of this stuff because you're going to want to do it real quick once you have something projected. You may have noticed that my bunnies don't look very good because once they're projected, you can see to the other side, so there's just kind of a whole mess of lines and it doesn't really look like a bunny anymore. So what can you do? Well, you can head over to Fogelman's repo. Fogelman is a prolific plotter Twitter person who has done wonderful things for the community, and pretty much everyone I know who's wrote a path planner or an AxiDraw client or anything has started with Fogelman stuff and sort of ripped it out and made it their own, so it's a really good educational thing. And in what it can do, it's a line art engine. It's meant specifically for plotters. It can do the projection for you. So if you look at the code here, you're setting up the position of a camera, you're setting up the field of view, which is sort of a proxy for the focal length and the width and how far away you want to be able to clip things to. But then you're also passing in this renderer that you have to pass it some, in addition to your wireframe paths you want to draw, you have to pass it a wireframe that it can use to occlude things. So you can pass it like a mesh, and it won't draw lines that are on the other side of the mesh from the camera. And that's hidden line removal. And then it also does texturing. Do you have a bunny, but you wanted to have contour lines around it instead of just the wireframe itself? This can do it. So really educational. Go read through the code, see what's there. This code right here just renders a square. It's pretty easy. It can output to SVG, and all the plotter tools can plot from SVGs, so it's very cool. Someone just ported this all to JavaScript, someone on Twitter, so you can do it all in the browser now. They're trying to get hooked up to 3JS. Like I said, no one really uses his Go, but everyone is inspired by it. And so, all right, this is a good book. I went to the library, I was looking for books on this stuff. One of the things I like about this whole plotter thing and the fact that it's pretty low level is you don't need new books. This book isn't super old, but some of them are, but you can find a book from the 80s, and it's going to have all the stuff you need to know to do pen plotters, because pen plotters were around in the 60s, right? So if you want a book that's not going to send you sidetracked into GPU land, which obviously I don't know anything about and I'm not interested in, I just want to do pen plotters, you can go buy look at these old books, and they're going to tell you everything you need to know about this sort of basic geometry stuff. This one's sitting out there. You can have a look at it. I laid out 3 textbooks on this subject if you're interested. And this is the slide that tells me I am done. So that is pen plotter projection. Cool.